Well, thanks and welcome back after lunch. I hope I can keep you awake after having food in your stomach. This might be tough. So as I promised, the second part of my lecture will be more about actually what we do in the lab after we found a topological material with the chemical principle I discussed before. And just to repeat ourselves, so what we were trying, we're connecting those properties to identify material first. And because this lecture will be later focused on 3D Dirac materials, I just wanted to remind you that we had the three principles of finding a Dirac semimetal, which is high symmetry, charge balance compound, and the good ratio between electronegativity and spin-orbit coupling. And before I talk to you about growth methods and what we do, I just want to have another motivation is why do you actually want to look for a new 3D Dirac semimetal? I mean, in my first talk, I gave the example of why we should look for topological materials in general. But also, a problem with known 3D Dirac semimetals is that most of them, or at least when I started looking in this field, they had the problem that the bands weren't really linear over a long energy range here. So if you make a real crystal and you have a real life problems, you will have defects in your structure, and I will come back to this later in the crystal growth section, and then your Fermi level can wiggle around and maybe not be in the point of interest. And then also, if you ever think of large scale applications, and we chemists do this a lot because lots of chemists work on batteries or thermoelectrics or other things, then you think about which compounds are actually cheap to make. And then you want to look in this part of the periodic table where the circles are large, because those are the elements which are actually abundant on Earth's crust and we have available, whereas like bismuth or whatever we all like for topological materials is not that abundant actually, okay? So this is another thing to think. And then also you might want to avoid toxic things like cadmium arsenide. I will tell a bit about the growth of cadmium arsenide later, but I always like to tell the story how I tried to grow it, and then I blew up a full tube of cadmium and arsenide in a furnace, and this is really not a good thing to happen to you, because then it oxidizes, and then you have volatile or dust, which is really, really, really toxic in this furnace. And so the only thing what you can do is really like wrap yourself in protective clothes and bag the whole furnace and throw it away. And so this costs money, this is not good for your health. So just for the sake of us chemists, we also try to avoid elements like cadmium or arsenide. And also maybe you might know sodium-free bismuth as a 3D Dirac semimetal, and this is so air sensitive. This is also for the experimental physicists, which among you might not be so much fun to work with, because then everything needs to be in a glove box, everything needs to be protected, like all the transfers are issues. So just the best materials to find should be cheap, non-toxic, non-air sensitive, and allow for defects and still have some room to play with the Fermi level. Okay, this is a cycle of life for a topological material. So basically, you have to come up with some ideas, and this is actually mostly done by theoretical physicists so far with an idea to look for. And then we chemists can do design principles like I introduced in my first lecture to come up with a suitable materials, or maybe there are also some prospects now, what Claudia mentioned with the recent paper from Andre and her in Nature with some theory approaches of finding a material. But once a material is identified, well, okay, if you do it in a chemistry principle, we just do it from structural ideas. If you do it in a physical one, this next step is already included. But anyway, so we calculate the electronic structure based on the crystal structure we thought about. And then we can go ahead and make it. And so I will talk about synthesis a little bit more in a second. And then this step here is extremely important, although I won't discuss it today, is the characterization of the crystal structure, because I mentioned it before briefly, not everything in the ICSD is correct, and not everything you make up might work the way you want to. So you really have to make sure whatever you put in, plugged in into your electronic structure calculation actually comes out here in reality. And then once then this red cycle here is complete, you can go ahead and measure the properties, or for example, do an ARPIS experiment or STM experiment or something to verify the electronic structure. And so this part of my talk will be focused on that step and that step. Okay, so once we have an idea of a compound we wanted to make, we have to try to grow a single crystal of it. So the problem is that because most of the methods that we have to verify, or all the methods we have to verify, electronic structures require single crystals. So now, I mean, we do have things like nano-ARPUs that you can look at really small crystals, but this is really hard to get beam time on those. And so most of the time, you want to have a large millimeter-sized crystal to actually verify the electronic structure in an experiment. And so there are different, so this are the 5 most common crystal growth methods. They're out there. And I just list 4, sorry. And I listed which topological elements are, or materials are usually grown with which method. And I will discuss the first three methods now in the talk. And the last one, the floating zone method, is actually the method which you have to use if all the other one fails. And this requires extremely expensive equipment, so which is why I, who can't afford such a floating zone furnace, usually tries to avoid this method and get along with the ones above. So that's why I'm focusing on that. So the first one I want to discuss is the vapor transport method, because this is an extremely easy crystal growth method, and if it works, it gets you really, really, really nice, really large, high-quality single crystals. And so if you can grow anything with vapor transport, except for a few exceptions I get into later, you should use this method, because it's really great to get really largely sized, high-yield single crystals. And so the way it works is that you seal solid reactants, so the elements or maybe a powder of the material you want to make, into a quartz tube, and you add some kind of gaseous transport agent. So this can be a solid or a liquid at room temperature and become a gas at the high temperature where you heat your container to, or it can be already a gas at room temperature. And then you heat this container, and you heat it to a different temperature where your reactants are, and you have another temperature at the end of your container. And so your solid phase forms an intermediate component with the transport agent, which is also a gaseous compound, and then on the other side of the reactor, you crystallize the phase you want to have, so this decomposes again. And so this temperature is often colder than the other one, so that you transport from the hot end to the cold end, but it sometimes works also the other way around, so you have to try a little bit. And so here I put the elements which often are parts of compounds that are easily to grow with vapor transport. So especially phosphide arsenides, sulfides, selenides, tellurides, and also halides can easily be grown with vapor transport. And then some oxosulfide or oxosanilides, pure oxides, might be difficult. And so here are some examples of famous topological or vial materials which can be grown with the vapor transport method. Okay, so now I said, okay, we put this mysterious transport agent, which is the gas, into the tube. So I just want to give you an overview of the most common ones you can use. So actually, most of the transport agents used are some of the halides. You have here like chlorine, bromine, or iodine. And basically, iodine is the easiest one to handle because it's a solid at room temperature. It becomes this purple gas if you heat it a little bit, but you can add a solid in your container. But it works really well for zirconium compounds because it forms an volatile intermediate with zirconium, and also some other elements. But with some other compounds, sometimes iodine isn't strong enough. Then you have to go to bromine, which is a little bit more nasty because this is a liquid and already makes this brown gaseous vapor, which is, by the way, very toxic when you handle it. So yeah, you can still do it. You can still put a liquid somehow in a tube, right? The liquid is still somehow contained. But then if you go to chlorine, because bromine also doesn't work, you really have a problem because chlorine is a gas, it's this green gas here, and it's super toxic, and you don't want to breathe it. So then there's some methods around it. So you could, for example, use selenium or tellurium tetrachloride because those decompose if you heat it to selenium and chlorine or tellurium and chlorine. And so if you want to make a telluride or a selenide anyways, then this is a great method to substitute it. Another thing you can use is ammonium chloride, which would decompose to NH3 and HCl, and HCl can also work as a transport agent. And so this is also salt. You can just put it in a tube, and it's a clean way to do a vapor transport method. And so there's a more advanced method of the vapor transport to get really, really beautiful crystals I briefly want to discuss. Because when you do a normal transport reaction, then lots of small crystals crystallize everywhere at the tube walls here. So you have lots of nucleation sites. Everywhere is a little small crystal. But if you put a small crystal you already grew in the first step as a seed there, you can grow one huge crystal around the seed. And so this is called the seed growth method. So this is here an example. They grew this copper oxoselenide with ammonium chloride as a transport agent. They put a seed growth here. Oops, sorry. And they get really this gem-like single crystals off the compound. And also what is nice if you use a seed is that you get less different crystal phases. So they showed that you get this 100 phase only at the places where the crystal is attached to the tube. And you get only the other phases, only the 110 phases of a crystal if you have a seed growth. So you have some methods even designing which crystal phases you get. So there's lots of control you can actually have with careful growth methods. Okay, so now I advertise vapor transport a lot, and it is a really great method, but it has some limitations. So one example is cadmium arsenide. There are lots of papers out there that grow it with vapor transport, and if they grow it with vapor transport, they get really, really nice, really large crystals. The problem is that if they measure transport on those crystals, they get a triple R ratio of about only 8, so it means the resistivity of room temperature divided by the one at low temperatures, the ratio is 8. And if you grow it with a different method, the Flux method, I will explain this method to you in a second, you get much, much, much higher triple R ratios. And so why is that? So only the one with a high triple R ratio show this really high mobility, what cadmium arsenide is famous for. So, and the reason is, so here, this is the phase diagram, the binary phase diagram of arsenic and cadmium. And on those phase diagram, you plot on one axis, you plot the amount of cadmium added. So here it would be just arsenide, there's just cadmium, here's the mixture, and here's the temperature. And then it lists which phases are stable. And so here, cadmium-free, arsenic-2, what we care about is along this line. And you see that over a temperature range, there are 4 different phases stable of cadmium arsenide. And the one we want is the one down here. So now if you look at the vapor transport reaction, they have a temperature gradient here from about 175 Celsius. So they span a lot of this axis, so there are lots of competing phases. So that means the large crystals they can have lots of grain boundaries between different crystallized and maybe even in different phases of cadmium arsenide. Whereas if you use a different method where you just carefully have just one temperature aligned to, you can have much better crystals. Another famous example where vapor transport kind of fails is tungsten Telluride, which is famous for its gigantic magnetoresistance. And even there, if you grow it with vapor transport, so you get low triple R ratios. So those are crystals here grown with vapor transport. This is the triple R, and this is the MR observed at 2 Kelvin and 9 Tesla. So with vapor transport, you're down here, low triple Rs, low MRs. And if you grow with a flux, then you get much higher MR ratios and much higher triple R ratios. And so the reason here for this is that if you grow from a flux, you use a lot of excess of tellurium. And apparently tungsten Telluride likes to form tellurium vacancies. So if you have a lot of excess in your flux growth, you can overcompensate that. Okay. So sometimes it's better to try a different method. Okay, so now I mentioned the flux growth method several times. And I want to explain how this actually works. So basically, it is a method where you have some liquid here, and this can be a molten element. So in tungsten Telluride, that can be liquid tellurium. And you also have the compound you want to grow in there. So you have some tungsten dissolved in liquid tellurium, but much more tellurium excess. And you cool, so you melt everything until everything is liquid, and then you slowly cool, and a crystal forms inside the liquid. Just like you would grow sodium chloride from water. It's a similar solution growth. And then, because tellurium is not liquid at room temperature anymore, you take this tube, this container out of the furnace when it's still liquid, so when it's hot, several hundred degrees, and you put it upside, so you had a filter in here before, and you put it upside down in a centrifuge to get rid of the flux, and then you have your crystals. Because the advantage is you have only one temperature because you quench from it. So in a compound like cadmium arsenide, you won't have competing phases. You have an excess of maybe one element, so you don't have defects from having too little of the elements. But the disadvantage of this method is that the quenching is also not really that great you can have defects from quenching from a high temperature. And also, putting it in a centrifuge and spinning it puts lots of strain on it, so those crystals can also have defects. Usually also flux-grown crystals are smaller than vapor transport crystals. So sometimes this can be better than vapor transport, but often it is a worse method to do so. However, there are lots of compounds you can grow very nicely with this method. So I already mentioned cadmium arsenide and tungsten telluride, but also other telluride-based phases can be grown that way. And iron-based superconductors are famously grown from fluxes. And also sodium-free bismuth is grown from a flux. So what can you use as a flux? So there are different ways of flux growth. So you can either use an element as a flux, like I gave with the example with tungsten telluride, where you use tellurium. And for those, you can use all those low melting elements, which are those ones in the periodic table. So those are all elements that have a low melting point, and you can use it as a liquid. And so, of course, you can grow phases which contain one of those elements from them. But you can also use a foreign flux. For example, cadmium arsenide can be grown from a cadmium flux, like here. However, I mentioned cadmium is very toxic. If you have a cadmium flux, you use like 10 grams of it. Maybe you don't want to do that. So you can also use, for example, a bismuth flux, because neither cadmium nor arsenide likes to really react with bismuth, and so it still forms cadmium arsenide, and the bismuth just forms as a liquid, dissolving that, and then as a flux, it doesn't really interact with the reaction. However, so in order to figure out which flux is good for you to use, you really have to carefully look at all the published phase diagrams between the flux element and the element you're working with and see if they form stable phases or not. So it requires a lot of literature looking to figure it out and try and error. Then you can also grow oxides from flux, like in this method drawn here. And this is nice because then you can use a salt flux, like sodium chloride, for example, or soda or something like this. And if you grow something from a salt flux, which is an oxide and usually air and water stable, you don't even need to centrifuge this because you can just dissolve the salt in water again and then pick out your crystal. And then this is here a method where you can use feed rods and just use zone melting with the flux, and this can be really used to grow extremely high quality large single crystals of compounds, but this is a more complicated method. And the last method I want to introduce is the Bridgeman method, which is actually an extremely simple method where you melt all your elements, the things you have, until it's molten, and you put the elements in the composition you want to get out later until you have a complete melt, and then you just very slowly cool the melt by slowly pulling your tube through a vertical furnace with different temperature gradients. And then you just get a single crystal. It's a super, super simple method. Okay, why don't we use it all the time? Well, we can only use it if our phase diagram, this compound has, like here, like bismuth selenide, one line which goes all the way down to the bottom. Because otherwise, if the line would stop here, then at this temperature, the phases would start decompose into different ones. So there's only a few number of materials you can grow this way, but if you can do it, it's really great. And so that's why bismuth selenide and telluride and all these topological insulators are grown really easily. Okay, so now we grew our crystals. So let's say we identified a material we care about. We grew the crystal. We can be super happy we have a large single crystal. Well, the next question is if it's actually going to cleave. Because I predicted materials before, and I grew materials, and then nobody could cleave them, and that's a problem trying to publish about it. So if you want to do ARPIS or STM or any of the surface-sensitive methods, you need to cleave your crystal in UHV, because you need to have a perfectly clean surface for the experiment. And so for this, you can glue the crystal with like Van der Waals things. You can even use Scotch tape, which is nice, but with lots of materials, they can't. The bonding is not that weak. But then you can glue a crystal on those little plates here and put a stick on top of it with another glue, and then put it in an ARPIS chamber and in UHV knock off the stick and hope it cleaves. It only works if your crystal bonds are weaker than your glue. So sometimes if you have a really strongly bonded material, it just doesn't work. And then you can do an ARPIS experiment, and if you're a chemist like me and you don't really know much about ARPIS, there's one trick you do. You hire a physicist student who can do it, and So I'm trying to give you a short introduction about ARPIS now, but for any in-depth question, I would refer you to talk to Andy. He's here and can answer the questions. Anyway, so ARPIS is a really nice method which basically lets us take a photograph of an electronic structure from a crystal surface. And it's an extremely surface-sensitive method. It's based on the photoelectric effect that you eject electrons with photons from a crystal, but you really see the surface band structure of a material. Okay, so how does it work? I mean, really the basic idea is the photoelectric effect, which is known since 1900 something, when Einstein got the Nobel Prize from it, that you can use photons to eject electrons from a material. And you can think about it in this three-step process, that at first your photon comes in, it kicks out an electron from its shell, then the electron somehow has to travel to the surface of the material and then leave it towards a vacuum. And actually, this is often the most critical step, that the electron just does something within the crystal and doesn't get out. And so this is the universal curve of the photoelectric effect, and it tells us about what our possibilities of ARPIS are. So this is a plot where here you have plotted how deep your photons penetrate into the material, so how deep the electrons are you can eject from it. And then on this plot is the photon energy you use. And so it looks like if you use very low photon energies that you can penetrate into the bulk of the material. The problem is, yes, photon gets in, but then the energy is too weak to actually kick out an electron. So you won't have the photoelectric effect, so you can't really use this low photon energies for ARPIS experiments. So your limiting factor is really not if your photons can get into the crystals, but if the electrons get out. And then you have this range here where you can really nicely measure ARPIS spectra, but you really only have a penetration depth of a monolayer of few, and this is why ARPIS is such a surface-sensitive method. And you could also increase the photon energy and get a little bit more bulk-sensitive again, but at some point the cross-section gets too small, so the photons don't really kick out the electrons anymore, and also the brilliant zone you measure gets way too small, so you don't see anything anymore. So the optimal range for ARPIS is about this kind of photons energies, and it's thus a pretty surface-sensitive method. Okay, so what we measure when we do an ARPIS experiment is the kinetic energy of the electron ejected, but we actually want to convert it to the binding energy to have an idea of how the electrons are bound in this and to get an idea about the electronic structure. And so this is a very simple conversion where you just take your photon energy and you subtract the work function and the kinetic energy you measure, and you're done. And by the way, this might be confusing. Some people like to plot the binding energy, some like to plot initial state energy. This is just the same with a negative sign. And the initial state energy is what you plot in a DFT calculation, so I try to refer to this one. Then the other thing we want to measure is the momentum, so that we can have really an band structure, not just a density of states plot. And for this, we can use the exit angle of the electron. And there are two angles we have. One is based on the detector already and the analyzer, which measures a range of angles of the electrons ejected from the material. And the other angle we are adjusting by tilting the sample during the experiment. And we can convert this angle with this formula to the momentum in the crystal structure. So this is a typical spectrum, what you would get just if you do take an XPS spectrum with just one constant angle. And you get this kind of curve with the different peaks. And you have to fit this curve first with the Fermi-Dirac function to model this Fermi edge here, and then with some Lorentz functions to get an idea of where the peaks are and where you actually have a density of states. And then there's also the so-called Shirley background, which comes from inelastic scattering within which needs to be subtracted. But nowadays we get immediately such an image out of an ARPIS chamber already, this two-dimensional image, or three-dimensional image if you take the scale here. And this is because we have now CCD cameras and better detectors which already measure all the angles based on the slit angle you have in the detector. And so each of the energy distribution curves I showed you before is like one line along this thing. So we immediately get this nice image out of an ARPIS spectrum. And then this image is at one given tilting angle of the sample, and you can continue to tilt the sample, and you can get more of those images, and then you can put them all together to get a full data cube of slices to have the full Brilliant zone measured of your compound. And then you can also make plots along different directions if you take a cut like this, of course. So this is just one path along the Brilliant zone. If you want to plot a different path, you can cut all your images here, and you get a different spectra. But note that here, the resolution of this spectra depends on how fine you tune the tilting angle and how many of those individual images you took, whereas if here along this one, you have a much higher, nicer resolution. You can also make a constant energy or Fermi surface plot. If you want to do that, you first have to figure out where your Fermi level is. So you take one of the individual EDCs here, and you fit it to the Fermi-Dirac function to figure out where the Fermi energy is located. And then you can take a slice through your data cube along exactly this energy and get a constant energy plot or a Fermi surface map out of this. And then if you do that, you also need to adjust this to the gamma point, because now you can see from your electronic structure, you know that this should be the gamma point in here, but this is not at 0, 0 like it was supposed to be. And this is because you never glue your crystal on perfectly flat. It's always with a tiny angle. It's never perfect. This is just a few degrees off. So then you have to correct this offset and shift the gamma point to where it actually is. And once you did that, you can use those equations we had before to convert the tilt angle and the slit angle into actually momentum space. And if you do that, you have to be a little bit careful, because the cube you measured is no longer a cube anymore after the conversion, because we have the sine function in here. And now if you would take cuts in which are not constant energy, so along like this directions here, then you have some kind of distortion in your spectra, and you need to do some extrapolation. However, constant energy cuts are always possible, because there this doesn't affect it. Okay, just to sum up. Oh, sorry, I forgot the last step. And lastly, so now you have your image here with the corrected, the angles are converted to momenta, but now you see that the 0 line here is not following exactly what you would expect for the gamma X line, and then you might have to rotate your spectra to fit to the Brilliant zone. And this is also a result of the crystal not being glued on completely perfectly flat. Okay, to sum up, so after you took all your ARPIS data, there's actually some kind of data analysis you have to go through, which is kind of tedious, just that you have to figure out your Fermi energy to adjust the spectrum to that. You have to find your alpha and theta offset to place the gamma point exactly at 0, 0. Then you have to convert everything, and then in the end you even have to rotate it. And then you only have a Fermi surface map, so it becomes even more complicated if you want to cut your data cubes along directions you didn't measure. Okay, so now I want to give you some examples of this full loop or full life cycle of a topological materials based on my research about how you really can live through the whole process from having an idea to find a free Dirac semi-metal or another topological one, and then making it and proving that it's actually one. And so this is a story about a material I discovered when I read this paper by Roald Hoffmann, and Claudia already mentioned his name several times and also tried to advertise you how great it is to read his paper, and I can just only agree, because he gave me a really great idea in this old paper he published in 86, sorry. And so in this paper he talks about square net compounds. So compounds where the atoms are in a square net, and Claudia also mentioned those pretty often, and that you can easily draw the band structure of them even per hand. And so what he writes in this paper is, okay, when you have a compound where atoms are arranged in a square net, you have those crossings here, and it was before people cared about Dirac electrons or anything. And so he just noticed that they often distort and gap out because there's some residual density of states at the Fermi level, so they don't like it. By the way, this is not necessarily a half-filled band in a non-isomorphic system, which is just a Dirac crossing. So it's not forbidden to be there, but it's just still energetically not favorable. So at first I thought maybe that doesn't help me because they seem always to distort and get away of this crossing. But then I also noticed, okay, this is not a completely half-filled band-forbidden crossing, so if cadmium arsenide exists, this could also exist. And in addition, they always have those kind of plots here in the paper where they say, okay, this would be compound X if it would crystallize in the zirconium silicon sulfide crystal structure. So that made me wonder, what is this zirconium silicon sulfide crystal structure? So I looked up the material. This was published in the database, was known in a powdered form, not yet a single crystal form. But it is a material where you have the perfect square net of silicon, so at least in the published structure. Also, I like this structure a lot because it looks like the material can cleave here. This looks like a spot where the bonds are weak. It's a layered structure. It is the so-called PBFCL structure, which Claudia already referred to as my favorite structure type, which is true. And it is, you can cleave it. It's a layered structure. And this is crystallizing in space group 129. What I also liked is it's really only made out of cheap and non-toxic elements, and the powder was reported to be stable in air, water, and even diluted acids. And then I already mentioned this before. This is a charge balance material. If you take into account the Zintel concept and the bonding, so it could be a perfect 3D Dirac semi-metal just by chemical reasons. So I went ahead and did the DFT and looked at the band structure, and I found not only does it have Dirac crossings, it also has some with a very, very, very large energy dispersion. So that's the last point I wanted to improve from 3D Dirac semi-metals, and it's also given here. But then it has much more than just one Dirac crossing in the Brilliant zone, which is something I didn't expect. And if you follow those crossings through the Brilliant zone, then you see that they form this kind of line. So this is the Dirac line node material. However, if you include spin-orbit coupling in the calculation, this line node gaps a tiny bit because the crossings are all along those directions here where you have only C2 rotation. So the C4 rotation in this tetragonal group is along the gamma Z where, where we don't see a crossing here. But because neither zirconium nor silicon nor sulfide are very heavy, spin-orbit coupling is not that large and the gap is relatively small, and the bands remain pretty linear and can still show similar effects. So the next step was to grow the crystal, and because this is a sulfide, this was on the list of elements I liked that I said which are good for vapor transport growth. This was the first method I tried, and so I put the elements together with some iodine, the easiest transport agent you can use, in a quartz tube. I made this end really hot, this end a little bit colder, and then I received really, really nice single crystals on the side of the tube. So that was nice because it worked well. And you get these large single crystals which can be several millimeter size. They have this platelet forms, and you can actually really cleave them like I suspected, and they have this really clean, nice cleavage planes. Then the structure characterization, which I jumped over to, but I want to stress how important it is to confirm that the structure is actually what it is, because this was reported to have a square net structure, but maybe it doesn't. Maybe it actually does distort slightly, so you have to look carefully for that. So we confirmed the single crystal diffraction that this compound is what it has, and what I'm showing here is the electron diffraction images where you see that this is the measured pattern and these are the simulated pattern based on the square net structure, and we have a pretty perfect agreement. We also did some high resolution TEM where you can resolve the individual atoms. So in here is the simulation, and here is what we actually see. And you see that the simulation based on the known structure is perfect, and we can see each individual atom where it's supposed to be. And then lastly, we did some SDN topography to get an idea about how many defects we have. So these bright spots are defects. And this scan is on the very, very first samples I grew before I improved the methods. And we already only had about one defect every 50 unit cells, and we could improve that. So this is actually a compound you can grow relatively defect-free. So then the next step was to measure the ARPIS spectra. And so you can see here the in-house data. By the way, here you see how the data looks kind of ugly and stepwise, which is because this is a cut along this angle we tilted. So it's not a smooth data. So the measured direction is here where we have nicer data. Anyway, so the purple lines here are the states we expected from the DFT to be there. And then the additional states here and here, which we didn't expect from DFT. So we see the large linear dispersed bands, but we also see other bands. So that made us wonder if our prediction was not completely correct. But before we gave up, we thought maybe this is because ARPIS is such a surface-sensitive method, and we did a DFT simulation of a surface where you can calculate a band structure of the slab of a material. And if you do that, you get a really, really nice agreement between ARPIS and DFT. So we can be really confident about the electronic structure to be correct. So what I like most, though, about zirconium silicon sulfide is not only the material itself, but the structure type, because this crystallizes in the so-called PBFCl structure type in space group 129, and this is a very common structure type. So although Hoffman wrote square nets like to distort, they're actually more common than you would think. And so there are more than 200 compounds just in this same structure type, but then there's so many more other compounds where square nets are there. And so the square net seems to be this common structural motif, what I mentioned in the beginning, what solid-state chemists like to look for in crystal structure to link it to properties that we can link to this linear band crossings. And so here's just a very small table of compounds that are directly related to zirconium silicon sulfide and isoelectronic, but there's so many more out there. So now there's a huge family of compounds to explore for those kinds of physics. And this will give me, bring me to my second example, which is about how we can use this family to realize some of these non-symmorphic materials I mentioned in my last talk. And just to recap really quickly, the problem with non-symmorphic materials is that we require this half-filled band to have the Fermi level here. So the line node in zirconium silicon sulfide is like this one. The Fermi level is supposed where it is at the Dirac point in a charged balanced electron count. And so it is fine to be here. However, in non-symmorphic 3D Dirac semimetals, we would expect the Fermi level to be up here and the non-symmorphic crossing below the Fermi level. And so when I was thinking about non-symmorphic materials in the beginning, I actually had my doubts at some point that this is even real. I have to admit it. So I thought, okay, this looks all nice on paper, and you can write down in Hamiltonian on paper and it looks great, but then nature often does some crazy thing you haven't thought about and evades it. And so I actually questions if those non-symmorphic sticking points, how you call them, they are there in reality, or if nature does always something to evade them. So I thought I first want to take a step back and realize a non-symmorphic Dirac cone below the Fermi level, which should be easy to achieve, where the electron filling is up here, and we have a normal charge balance system. And then in the second step, worry about shifting the Fermi level to where it's supposed to be. And for this, I only need to find a compound where this crossing is not minus 4.5 eV away from the Fermi level, like in silicon dioxide, but a little bit closer, so it's accessible with ARPIS. And so this step A was actually already realized with ARPIS, with zirconium silicon sulfide, sorry. Because this crystallizes in this space group P4 over NMM, or space group 129, where you have a glide plane which is running perpendicular to the cleavage plane of the material. And because of that, you can see that here you have this non-symmorphic forced degeneracy at the X point below and above the Fermi level. And this one is not that far away, so we should be able to see it with ARPIS. And so here you see some nicer data than I showed you before, which were taken at the synchrotron, where you actually really beautiful see the non-symmorphic crossing point here at the X point, where we expect it to be there. So those features are there, they are real, they're not just made up. So that was nice. So then I was wondering, okay, can we shift that to the Fermi level? Can we somehow avoid the problem of half-filling and do something about it? So of course you could try to either electron dope or hole dope this material and then shift the Fermi level to this Dirac crossing, but then you see you cross through lots of different bands because you don't want to have an isolated half-filled band, you will have a half-filled band with lots of pockets. So if you ever want to do a transport experiment and you cut through other bands and you have dopants in it, this is just going to be a mess and you won't see anything. So I thought maybe I can just trick the system and use a chemistry trick to modify the electronic structure different. And this is often electronic structures are affected by strain or pressure. And a pressure or strain experiment to be done in reality is extremely complicated. And I don't know if you can even do an ARPIS experiment on something which is under pressure because it goes through diamonds and everything, the photons. So I thought maybe we use something which is called chemical pressure, which is actually a very common concept in chemistry, where you substitute an element with a different element which has a larger size, right? We were talking about the radius and the sizes before, and because this element is larger, it strains the whole material. So I wondered, okay, maybe we look at those compounds first here, and see, you can substitute sulfur with tellurium here. This is different sizes, and therefore we can play with the chemical pressure. First, we did that in theory. So we calculated the band structures of all those materials, and we looked at the energies of the Dirac crossings, and we looked at the C to A ratio of the compounds. So those are tetragonal materials, so they have a larger C axis than an A axis. If you take the ratio of C over A, you have some kind of measure for strain or pressure, because the material strains if this ratio changes. Whereas if just both axes increase the same, you don't really have some kind of uniaxial strain difference. And so you can see that most of those points, so the C to A ratio is plotted on the x-axis here. So most of those points, most of the materials fall into this very narrow window of the C to A ratio, so there's not much happening. But then there are two outliers here with a much larger C to A ratio, so it means they have a much larger C axis than an A axis in compared to zirconium silicon sulfide. And so if you plot on the y-axis, then what happens to those Dirac crossing or those non-isomorphic crossings, if you increase the C to A ratio, you can see that they come closer together in energy. That happens. And then for zirconium silicon telluride, it looks like this upper crossing, which is the blue points here, will hit the Fermi level right away. Okay? Just to point out, we just pushed it there with this method. So if this is real, this is not a half-filled band or anything. This is just a trick to push it there, and we didn't pin it with a Fermi level with an electron count. So here you would see the bulk band structure of zirconium silicon telluride. So you have this non-isomorphic crossing right here at the Fermi energy, and you do have pockets, because this is still a charge balanced compound, so this needs to have as many electrons as hole pockets, which stabilizes the whole thing, but the crossing is exactly here at the Fermi level. So it's just tricked to be pushed there. And so again, we could grow the crystals and verify the crystal structure to be the perfect square net. And the crystals now a little bit different because they're even more two-dimensional. You see the layers already peel off under this microscopy image here. So now you can scotch tape the materials, and you don't really need to glue and stick onto it to cleave it. And then if you take ARPIS spectra, we first thought we look at the constant energy plot or the Fermi surface, and then this non-isomorphic crossing point should appear as a dot here at the x point. And we did that, we see the second one, the lower one at minus 300 milli-electron volts where it's supposed to be, but the one directly at the Fermi level here, there's not really a dot, this is a circle, so that means our Fermi level is not exactly there where DFT wanted it to be, which can be normal because compounds are often hole or electron doped a little bit in reality, right? There's some defect. So we took some cuts through the momentum space and compared it again with a slab calculation. So the feature we're interested is this red-shaped rhombus here, where the Fermi level cuts the upper non-isomorphic cone right here. And so we can see this feature in the ARPIS data here, and we see our Fermi level is slightly lower than we hoped it was going to be, so the samples are slightly hole-doped. And so this is nice because then you can play a trick. You can just evaporate some potassium on the surface of a material, and potassium is very electropositive, so it injects some electron into the surface of the material and therefore raises the Fermi level a little bit. And so then if you do that, you really clearly nicely see a non-isomorphic crossing point at the Fermi level right here. So I just wanted to tell you the story to tell you this is possible to have such a non-isomorphic cone at the Fermi level. This is not isolated, this is not clean yet, but it's the first step. At least we show we can do it, okay? And maybe we can use this method of chemical strain and pressure of tunability to tune more of this other fold degeneracies there, and not only think about electron counting. So then lastly, I thought now since we established that square net materials are nice materials to look for direct physics and linear dispersion, maybe we can do the last chemistry trick and think about making those materials magnetic. Because, obviously you all know that magnetism breaks some kind of symmetries, can break time reversal symmetry, can also add some symmetries if it's anti-ferromagnetic order, and so we can change a lot of the band structure and tune a lot if we make a material magnetic. And so from chemistry, we know that certain elements order magnetic, and we also know which elements, it's not the best picture I'm showing here, but so for example, the rare earth elements and the ones up here, they're known to often order magnetically in compounds. So I thought I want to look for materials where those elements are present, the first thing to find a magnetic square net compound. And so if you look at the table, again, here I had at the beginning, here are some of those compounds where they contain rare earth materials. So I thought maybe it's worth starting to look for those because there's the rare earth and it could order magnetically. And so here's the electronic structure of the lanthanum version. So the lanthanum one is not magnetic. Lanthanum is just a normal non-magnetic element. But you can see in this non-magnetic simple calculation we did that we have the non-isomorphic crossing close to the Fermi energy here at X like before. And we have a Dirac crossing here along gamma Z. And so the question is, if we now add magnetism to this, what does it do? So I started with just making the first member of the series there, which is cerium, antimony, telluride, and see what happens. And so here, I just want to point out that it is important to look that the structure is what you hope it's going to be. Because if you look at the database, there were 2 reports of these compounds, one in P4 over NMM, and one in PNMA, which is not the space group we're looking for, where the square net is actually distorted. And so we did lots of different experiments to verify it's the one we want to have with the square net, the tetragonal space group, but I'm just showing the one here. You can see that this is a measurement, and in the PNMA space group, we would expect to see little spots between those ones, and we really don't see them, whereas here, they're missing. Okay, this is just one proof that this is the correct space group. We also did neutron diffraction, single crystal diffraction, powder diffraction at low temperatures, everything to verify that. Okay, and this was important because actually not all of these rare earth antimony telluride compounds are tetragonal. We tried others as well, and they are not. So they like to form this orthorhombic structure. Okay, so now we made the compound, and now we first needed to verify, was our idea correct? Does this actually order magnetically? It could still just be a paramagnet, then we don't really gain anything. And so this is the magnetic susceptibility at low temperatures, temperature dependent, and you see if you don't really apply a high field, just 100 or 1000 Ørsted, you get this really nice cusp in the data, which is indicative of anti-ferromagnetic order. And then if you apply higher fields, all of a sudden this cusp disappears and this flattens out more, which looks like ferromagnetic-ish. It's not a proof yet order, but maybe an idea. And we also see this field-induced transition in the field-dependent data. So this is magnetism versus field. And you see that at some critical field, this the magnetization jumps. So this is an indication of a so-called spin-flop transition, that spin flops from one direction to another one. And this spin flop happens at low fields if you align the field along the z-axis, and if you align it perpendicular of the z-axis, this happens much weaker and at higher fields, but it still happens in both cases. And then we also investigated with a specific heat. You can also see a magnetic transition in the specific heat, and you see the transition nicely at the same temperature here without a field, and then if you apply a field of 1 Tesla, this shifts slightly to the left, which is an indication of antiferromagnetic order, and then for higher field, this shifts to the right, which is an indication of ferromagnetic order. So you can also see the spin-flop transition in the specific heat data. Okay. So then we needed to solve the magnetic structure if you want to calculate any band structures of this. So in a ferromagnetic case, it's easy. All spins just point in the same direction, and we saw it was soft magnetic, so they point in the direction wherever we point the field. So we can easily simulate with the calculation, right? We point the field along the z-axis, all spins go up. Point it along the AB, they all go in this direction. But in the anti-ferromagnetic case, there's so many options. And so if you want to do a DFT, you need to know how the spins are aligned. So they could be antiferromagnetically ordered within the square net, or they could be just up in one square net and down in the other. In order to solve that, or to understand what the magnetic structure is, we did neutron diffraction together with the neutron facility at Diamond. This is a wish beamline at ISIS, and we had really, really great collaborators, like especially Fabio Orlando, who helped us a lot with solving the structure. And so he solved the structure in a way, so he figured out what we have is that we have ferromagnetic aligned spin in each of these layers where cerium is, and then they align anti-ferromagnetically to each other, and then this bilayer here couples ferromagnetically with another bilayer. And because of this, the whole unit cell doubles. Okay, and we can see that because there are extra magnetic peaks appearing in the neutron diffraction data, and they can fit it really perfectly. So here's the magnetic phase diagram of the whole compound. So at low temperatures and low fields, we have an anti-ferromagnet with a double C-axis, and then at high fields and low temperatures, we have a ferromagnet, and then up here we have a paramagnetic region of the sample. And so then the question was, what does this do to our band structure? And at first we just looked at what it does to the non-isomorphic degenerate crossing. So this was done with Maya here, and she did a really nice job with a group theory analysis where she looked at the high symmetry points and looked what the forced degeneracy do in each of those magnetic phases. And so you can see, so this was the paramagnetic phase, and we see like in zirconium, this is the same as zirconium silicon sulfide. We have fourfold, the possibilities of fourfold degeneracies at X that I discussed before, but also at the other points. And then if you add magnetism, you change a lot of those degeneracies. So there's lots of splitting. You can have only two folds here in the ferromagnetic cases. But what we like the most and was kind of surprising for us is that she found that there's a possibility of having an eightfold degeneracy in the anti-ferromagnetic phase. And once we realized that it actually makes sense to us because we double the C-axis in this magnetic order, we add another non-isomorphic symmetry element here. You see this kind of translational symmetry with the spin coming up here. So this is just so we basically stumbled across that we can use anti-ferromagnetic order to even add non-isomorphic symmetries to materials where they're not there before. And so here we could verify all the group theory prediction Mayas did with the DFT. So we see the splitting, for example, here at the X point in two folds. If we apply a ferromagnetic case, and we find the eightfold degenerate point at the A point, sadly very far away from the Fermi level, so it's not just yet applicable, but we're just starting with this idea of using anti-ferromagnetic order for this, so we can use this in the future. And then lastly, this was all theory so far, and this was an experimental talk, so we also did some ARPIS experiments. The problem with ARPIS is that it's not really applicable to do ARPIS in a ferromagnetically ordered phase or where a field is aligned, because the electrons you eject are going to be deflected by the field. So this would be something for an STM experiment, and maybe Chaim will talk about this possibility tomorrow. But we did some ARPIS on the paramagnetic phase where we don't have any magnetic order, and we could confirm the basic features in the electronic structure to be sure that we at least didn't make a complete random prediction here. And with this, I want to conclude in a summary and say that square net compounds are great materials to look for Dirac and Weil physics. And we could show that we can have line node materials in zirconium silicon sulfide. We can have non-isomorphic crossings in those compounds below the Fermi level. We can play chemistry tricks with pressure or chemical pressure to move those crossing points to where we want them. And then we can also make those materials magnetic. Thank you very much for your attention. Oh, and now I want to thank everybody involved in the work. Mm-hmm.
And so then I was wondering, is this kept under control when you make your ARPS experiment and look at bands and interpret the result, and you systematically do this, accounting the fact that there are impurities, or is it that do the impurities affect a lot this shapes of bands and small details you try to figure out?
Well, it very much depends. So first of all, you have some control of the defects in the crystal growth, not complete. Some will always be there, but you can grow better and worse crystals. But then also for ARPIS, usually defects are not that important because you average over a large portion of a crystal. And so it's the same like in a diffraction pattern. You see the average spots, right? You see the average picture. So like defects is really a local problem. So if you do any local probe, then a defect might have a huge impact on it, right? So then you have to be careful.
Mm-hmm. What about temperature? I guess
Mm-hmm.
stuff that do it. And what do they, let's say you have this experiment at room temperature, what do you see?
Well, actually, some of the ARPIS data I showed were measured at room temperature, and yes, so of course DFT is a zero temperature method, and if you want to compare it, that is often why there's some disagreement. If you go up in the temperature, also the bands get more broad at room temperature, so you get much nicer ARPIS data at low temperatures, but you don't always get beam time at, there are some facilities that can go to 1 Kelvin, but it's not that often available, and often you use like 70 Kelvin or even room temperature. It really depends on how good your crystals are. I think actually the quality on your ARPIS data is more affected by your crystal quality than the temperature, but maybe somebody disagrees with me, but that's my experience so far.
How difficult is to, let's say, make these crystals already shaped? Let's say, like for example, nanowires or 2Ds.
Oh, well, this requires much more complicated methods. So nanowires, sometimes you can do it by really just getting a seed and grow along a wire, but often you need to grow it out of a solvent then and use a surfactant, which makes this kind of shape growth in a wire. And 2D things, then you have very different thin films methods like MBE growth or other things to make that. And this is, I mean, MBE is great, but it's super slow. Like it takes a long time to make really nice samples, and like you can just make much more material with.
Yeah, but do you think that it's possible to grow this crystal with MBE?
I think so, but you need to figure out, you need to have all the tuning parameters on your MBE. Then sulfur is very volatile. MBE is usually good for oxide compounds. So maybe also with chemical vapor transporters, physical layer deposition. But so some thin film person once told me that the thin film growth is always 20 years behind the bulk growth. And that's because it's so much harder to adjust the parameters. Semi-metal. Yeah, actually, so the transport experiments we did so far are super ambiguous. So I can't. So based on theory, there should be, but we're not really sure because it looks like a semiconductor in experiment, but we're not so sure if this is a contact-resistant problem so far, or so I can't give you really a nice answer to that yet. Well, because there's still bands, there's still pockets cutting the Fermi level. But for some reason, we see a jump up when the magnetic transition comes in the transport. So it's still, like, transport data don't make any sense to us right now. Maybe I can give you a better answer in some more time.
When you were talking about phosphor methods, you said that it's basically a quench to get the sample to crystallize. What's the general time frame for a whole grain?
About 10 days. So you heat it up within 12 hours, and then you let it sit in the all liquid state where everything is liquid for about 24 hours. So you make sure everything is well mixed, or 24 to 48 hours, and then you cool with about 2 or 3 degrees a minute down to wherever you want to quench it from. And this can be like a 200-degree window or 600-degree. It depends how long your cooling range is, and then